All right, and here we have a What the Physics video on the Reiter packet 5, that's friction. Example 2, static versus kinetic friction. Ooh. Our learning target is I can distinguish types of friction and solve for each using the fun equation. So we have a 0.5 kilogram book on a level table. Nothing is touching the book except for the table. The coefficient of friction between the book and the table is 0.6. So let's go ahead and list out our variables and draw out our FBD. So let's see. Let's do gravitational force. Gravitational force is always there because we're on Earth. So gravitational force. And let's see, it's sitting on the table, so that is going to be a normal force. And they seem to be the same size on purpose because it's just sitting on the table. It being the book. The book is not floating up in the air or falling downwards. So now let's go ahead and list out our information. There's no other indication of forces on it just yet. I mean, we'll talk about the frictional force, but for right now, we're just going to list out the information. So because we're trying to find the normal force, yes? So the mass is 0.5 kilograms. Yeah. And the gravitational force is, well, that's just equal to m times g. Okay, and so I'll solve that off to the side. We don't know normal force. I do have static friction. That's going to be equal to 0.6, although we're not really using that just yet. So let's go ahead and draw out the net force equation. Oops. So let's go ahead and do the net force equation for the y-axis. Oh, stop that, you goose. Net force equation for the y is equal to mass times acceleration on the y. We already mentioned it's not floating or falling, so that's going to be 0, which means the net force equals normal minus gravitational, which is equal to 0. So that means the normal equals the gravitational, which is equal to m times g, as we mentioned earlier. Yes, exciting. And let me go ahead and plug in. I've got 0.5 kilograms times g, which is 9.8 meters per second squared. And I tap that into my calculator, and I get each of these is equal to 4.9 newtons. 4.9 newtons. Now, gravitational force we already implied is upwards, hence this arrow upwards. And, or I'm sorry, I said gravitational and I was drawing in normal. Silly fair. Well, they're both equal to 4.9 newtons. It's just we're using the free body diagram to tell us which one is going in which direction. Okay, that was it for part A. Let's move on to part B. If you push horizontally on the book with a force of 1 Newton and the book doesn't move, what is the force of static friction? Foofs. The foofs exerted by the table on the book. So now I have an applied force going to the right, some type of applied force. And we said that's equal to 1 Newton, so we'll go ahead and write that in, 1 Newton. You say, oh, fair, where did all these numbers come from earlier? Well, I wrote them in early because I knew we'd be solving for them here, and I just kind of continued on, right? Because the normal force is always going to equal the gravitational force here because there's only the 2 forces on the y, and because there's no acceleration on the y. And of course, mass times g is always equal to gravitational force. But these other guys might change, so let's go ahead and mark them in, yes? Yes. So we have some type of frictional force. I don't know how big it is yet, but I do know the object is not moving. So I'm going to have, if there's only the 2 forces, I should have those horizontal forces the same size. But I should still prove that, yes? So I've already done the whole net force on the y-axis. That was up here. So I already have the whole 4.9 and the 4.9. So I'm going to now focus on the net force on the x-axis. Because the whole point in drawing out my free body diagram other than to visualize all the forces going on, is so I can draw out all my forces. So I can make my Newton's law statement. So force on the net force on the x equals mass times acceleration on the x. And we already said the book is not moving. So that means this is going to be 0. So net force on the x is equal to, well, let's see, I've got applied force. I'm saying that is to the right, so I'll make that positive. And my friction is to the left, so I'm making that negative. I can say force friction static if I'd like. Anyhow, that's equal to 0. So just like what we had done up here, I can say, hey, there's one force minus the other equals 0. Guess what, folks? Applied force equals frictional force static. Yeah, which is equal to 1 Newton. 1 Newton. Okay, so in the case where I am simply pushing the book to the side with 1 Newton, and the book isn't actually moving, that means my frictional force is equal to 1 Newton. Ooh, I wonder what would happen. What would happen, folks, if I pushed it with not 1 Newton, but with 2 Newtons? Oh, okay. I've got my exact same free body diagram that I had in part A. It's got a normal up and a gravitational down. This time, however, I'm pushing with 2 Newtons. Okay, so I'm going to make that longer. Now you say, oh, fair, man, that arrow, that purple arrow seems to be bigger now than the blue or the green arrow. Yeah, I should draw them out to scale for the same axis. For different axes, you don't have to be quite as picky. Okay, it would be lovely if I could draw it out beautifully and use some type of computing device to measure it all, but I don't have lines marked out on here. So let's see, it still doesn't move. Okay, oh, change color. And you didn't actually change color. Red, you goose. There it is, red. And that's going to be the force of friction. So my applied force is going to be the 2 Newtons. That's interesting, it disappeared. 2 Newtons. Okay, 2 Newtons. And now my frictional force is going to be, that's my question mark. Oh, why aren't you writing in the correct color, you goose? There's red. Yay. All right, so net force on the x is equal to mass times acceleration on the x. Once again, that's not moving. So I'm going to have my net force on the x is equal to, hey, this is the exact same equation I had before. Ooh, 0. So once again, folks, applied is equal to frictional static, which is equal to, in this case, 2 Newtons. You mean if I keep pushing and the object isn't moving, the forces are going to stay balanced? OMG physics, yes. All right, D, what is the maximum force? The maximum force of static friction. Okay, same exact situation as before. But, I don't know my applied force. I don't know my frictional force. If only there were some other way I could come about the frictional force. But wait, there is. Up here, we said static friction is equal to 0.6. Oh yeah. See, static friction actually varies from 0 all the way up to 0.6. 0.6 is the maximum coefficient of friction. Ooh, yeah. So what we're trying to do is we're trying to figure out the force of friction there. Ooh, yeah, nice. Okay, so if I'm gonna have to incorporate this coefficient of friction, then the only equation with coefficient of friction in it is the fun equation. Force of friction is equal to mu times force normal. So let's go ahead and plug in for that, yeah? Because we have the mu is 0.6, 0.6, and then the normal force we have from before, 4.9 newtons. And I'll say this is max. Okay, static. Okay, so I guess I wrote Fs that way. Max equals, tap, tap, tap. I've got 2.94 newtons. 2.94 newtons is my maximum static friction. That's your maximum static friction. I wonder what would happen if I pushed with a larger applied force than that. Oh my goodness. Oh my goodness. Oh, you know what? Silly fair. You forgot to draw in some of these forces, yeah? That means my maximum force of friction would have been that way, and my unknown, until I just solved for it, it would have been 2.94 applied forces that way. Now, let's say if I pushed with a force even greater than the static friction, what would happen? Well, if I push with a force greater than 2.94 newtons, the object would start moving, right? Yeah, let's say we push with 4 newtons worth of force. 4 newtons? Oh no. Say, oh yeah. So here's some type of applied force. I'm going to use 4 newtons because I'm crazy, folks. I'm crazy. And then we have a frictional force going this way. Okay? If we can push hard enough to overcome the static frictional force, then that means we're going to turn it into kinetic friction. So if I use 4 newtons, notice that's going to be larger than the maximum static frictional force. So now I got to figure out what this guy is, yeah? I know, because I'm just going to use 0.4 is my coefficient of kinetic friction. So once the object starts moving, we're no longer using the static friction that maxes out at 0.6. Once the object starts moving, the force of friction is always going to be a fixed value. With the with the kinetic coefficient of friction is 0.4. So what I'm trying to do now is solve for the kinetic friction. Ah, okay. All right, I gotcha. Let's do the fun equation, because we do have to solve for the kinetic frictional force, yeah? Force friction is equal to mu times force normal. That's going to be 0.4 times 4.9 newtons. Let's see, put some parentheses around that so it's not too confusing. That's force of friction kinetic. Force friction kinetic is going to equal, let's see, tap, tap, 1.96. You said 1.96? Wait, are you serious? 1.96 newtons? Isn't that smaller than my maximum static friction? Yes. Yes, it is. Ooh. So your maximum value of your maximum value of your static friction is going to be larger than your kinetic friction, which is going to be a constant. Kinetic friction is a constant. So from here, I could go ahead and solve for, if I wanted it, I wasn't specifically asked for this, but I could go ahead and solve for the forces on the x-axis, mass times acceleration on the x. And in this case, the acceleration is not equal to 0. So I would go ahead and say force applied minus force of friction, that's kinetic by the way, is equal to mass times acceleration on the x. And then I could actually plug in some of these values. I'd get 4 newtons minus 1.96 newtons is equal to the mass times the acceleration. Now if I divide through by the mass, which is, gotta scooch this paper around, 0.5 kilograms, I'm going to get acceleration is equal to, oh, stop that, you goose, 4.08, and that'd be meters per second squared. Oh yeah, there's some physics for you, right there. So what we did was we went through, this is a standard non-angled force setup. We set up the free body diagram with the normal and the gravitational. In these cases, they happen to be equal. They won't always, but they happen to be equal in this case, because there's only the 2 forces and there's no acceleration on the y. So that means I know what the normal force is. And as I kept increasing the applied force, the static frictional force kept increasing until I got to the maximum value of static frictional force. And then I said, well, what happens if I pull harder than that? If I pull harder than 2.94 newtons, then I've got some actual motion. And what is that actual motion going to be? Well, I can solve for the acceleration and get it that way. Yeah, AP, if you go on to take AP physics, AP does this, and they're sneaky about it too. They'll be like, oh, yeah, what happens if you push on it with this much force? And yeah, you got to check to see if it's greater, if the applied force is greater than the static frictional force or not. Always check that. Good stuff. Good physics.